G'day chemists. So let's have a look at the characteristics of a system at equilibrium. So this is our learning goal. We want to be able to understand the characteristics of a system at equilibrium, right? That makes sense. That's what the video is about. But by the end of this, we should be able to, if given a description of the properties of a system, determine if it's at equilibrium. Yes, that meets all the criteria, and away we go. This is your vocabulary. If I can just get you to pause the video here, write this down, we'll have something to refer back to as we move forward. So let's look at how we break different types of equilibria up into separate classifications. First off, we look at the symbol used. Okay, so where to separate both sides of the equation. The single arrowhead talks about a reaction which is non-reversible, which can still be at equilibrium, or we have the reaction which has the double arrowhead, and that is a reversible reaction. So when we have the single arrowhead, we have a static equilibrium. So when we set magnesium on fire, we burn it with oxygen, it goes to completion, and that achieves a static equilibrium eventually. So it's a complete forward and reverse both at the same rate. So the forward reaction and the reverse reaction are happening at the exact same rate, and that is, to be honest, they've stopped because it's gone to completion. It's a closed system, and the concentrations are constant. In other words, the concentration of the reactants and the concentrations or amounts of the products are not changing. And that's because the reaction has stopped. Or we can have a dynamic equilibrium, which is where we would use that double-headed arrow. So if we go from nitrous oxide to dinitrogen tetraoxide, we have a dynamic equilibrium. We can see that we have the double-headed arrow, and what this means is that the reaction's incomplete. The forward and reverse reactions are both happening at the same rate. In other words, it's going forward and it's going in reverse at exactly the same rate, so it looks like nothing is changing. It's a closed system, we've got a lid on there, and the concentrations are constant. Because both reactions are happening in the same direction, the concentrations of the reactants and the products are not changing. Now, we can also break our equilibria up into heterogeneous equilibria. So this is where we have substances of different states of matter. For example, if we look at the lead iodide solubility equilibria, we have lead iodide on one side as a solid, and we have lead ions and iodide ions as aqueous substances. So we have different states of matter. So that is a heterogeneous equilibrium. Here we have another example, which is the dissolution of carbon dioxide gas from the air into the water. And we go from a gas to an aqueous solution. That is a heterogeneous equilibrium. Or we can have homogeneous equilibria. For example, all substances are the same state of matter. The nitrous oxide into the nitrous dinitrogen tetraoxide is a homogeneous equilibrium. So is the acetic acid in vinegar. So acetic acid is a weak acid, which means it exists in equilibria. So we can have acetic acid dissolved as the acetic acid molecule, but some of that will ionize in equilibrium to give us acetate, so that's the CH3CO minus ion, and the H plus ion. So here we have a homogeneous equilibria. Let's have a look at the characteristics of equilibria. We're talking about either one here, but we're using the double dynamic equilibrium symbol just because that's the one that more often than not we associate with equilibrium reactions. So it's going to be a closed system. This means that energy can leave and enter for sure, but matter cannot. Matter can't move in and out. So there are no matter moving, and there's no net energy movement. So what this means is, as energy leaves, energy comes in because it's at an equilibrium with the system itself and the environment around it. Macroscopic properties remain constant. These means the properties that we can see. Okay, so pH, state of matter, color, pressure, temperature. They stay the same. They're now constant. The forward and reverse reactions are equal. For example, as we move along this axis here, we have time moving in this direction and rate of reaction up here. The top line is our A to B, so forward reaction. This is our reverse reaction. And here our reverse reaction is starting at 0. Top reaction is all of it. And eventually they reach equilibria where they're both moving in a conjoined line. Now we see that we can actually look at our forward and reverse reaction as we can look at it from either direction. It doesn't really matter. So we can look at it from A plus B goes to AB over here, or we can go from AB goes to A plus B. It actually doesn't make a difference. What's important is that we write it down, so when we refer to it, we have a direction there. Both directions occur on the atomic level constantly. In other words, they don't stop, like they're constantly moving backwards and forwards. And both concentrations remain constant, but not necessarily equal. They can be equal, but they don't have to be. So as the reactions are happening in both directions at all times, the concentrations are not changing. So as one goes this way, so as the forward reaction happens, the reverse reaction happens at the exact same time, and they stay constant. And we can see how it all interrelates. And if one of these conditions isn't met, we don't have a system at equilibrium. I hope that made a lot of sense. If it didn't, if you have any questions, put them in the comments and we'll get back to you as soon as we can. Thanks for watching. Don't forget to subscribe so you can keep up with what we're doing. And we'll see you next time. Bye now.